It's a pleasure to be here yet again, and I thank all concerned for the opportunity, invitation and the opportunity. What I'm going to talk about is the indicated in the title, Diophantine approximation with non-singular transformations. That's the title. Even if it may not be entirely obvious what that means, will soon come to that. So here is an old result, sort of slightly modified version of an old result. So which I'm now going to talk about. Say we will denote by gamma the semi-group of non-singular integral n times n matrices. So you take n times n matrices with integer entries and determinant non-zero. So non-singular I said. So then that is a semi-group. It need not. It is not a group, because if you take an integral matrix with determinant other than plus or minus 1, the inverse is not going to be there. So we are going to consider the action of this on Rn and later on more generally on copies of this. So if I start with a vector v in Rn, the orbit is dense under certain conditions, and the conditions are very simple. So long as this vector v is not a multiple of a vector with rational coordinates, then the orbit of gamma, do I have a chalk here? You have, I'll draw only the two-dimensional picture. So you have R2 and a vector v here, and you are taking the orbits of this. So there are different, so gamma 1 v, gamma 2 v, etc. And so on. And the fact that is recorded there is that if the slope of this, I mean if the is irrational, it's clear that if the slope is rational, then the orbit is actually going to be discrete, because the denominators cannot will have a bound, so they cannot go to infinity. There on the and conversely, if the slope is irrational, then the orbit is dense. This is a result in the thesis of Sreekrishna Dani, that's 1976. Later we, myself and Raghavan, improved this to take multiple vectors. So take v1, v2, vp. So each of them is in Rn, and now look at the component-wise action. Each gamma acts on this component-wise. So you get gamma 1, gamma v1, gamma v2. Gamma Vp. So that will be the action in the general case. Now in this case, you will notice that if you have a certain linear, non-trivial linear combination which is a rational vector, then again density is going to fail, because the same same linear combination is ever going to produce only rational vectors, and the denominators will stay bounded. The point of this theorem was the converse, that so long as your vector is such that this linear combination is not a rational vector for any non-trivial p tuple lambda 1, lambda 2, lambda p, then the gamma orbit is dense. Now actually I have done a bit of fudging. The original result is actually stated for SLNZ. I mean, so far there has been a practice of only looking at actions of groups. So SLNZ, but it's obvious that if you know the corresponding statement for SLNZ, then it is true for gamma. First of all, gamma is a bigger bigger object. So if for a vector v the SLNZ orbit is dense, then the gamma orbit is going to be dense after all. right? On the other hand, the complementary case was when there is a certain rationality condition that is satisfied, and once that is satisfied, you can see that no matter whether you're talking of the orbit of SLNZ or gamma, the orbit is not going to be dense. So the two are essentially close cousins of each other. So we can now start with saying that we know this thing. This again is quite an old result so far. I mean, it's nothing new, and subsequently there's a lot of development along these lines, and in the framework of what is called the Ratner theory. Many of you would have heard Marina Ratner, who made landmark contributions in the area of ergodic theory and orbits of subgroups on G mod gamma. So there, the general framework is the following: you take Lie group, SLNR is for instance is an example. Take a lattice gamma in that. Lattice means it's a discrete subgroup such that the quotient space has finite invariant measure. So, and the standard examples for this would be SLNR with gamma SLNZ, and in that case, and when you have this G mod gamma which is a space with nice finite measure is invariant under the action of the group. So then, in this context, the Ratner's theory started, in fact, with Raghunathan's conjecture, which I will not go more into the detail. There is a conjecture of Raghunathan about orbits of certain subgroups of G acting on G mod gamma, and saying that if the elements of that subgroup consist of unipotent elements, namely there are no eigenvalues of eigenvalues other than 1, then the closure has the property that the closure itself is an orbit of a possibly bigger group. So here and then okay, let me quickly write down. So since I have said it halfway, so you take G Lie group, gamma lattice, H a subgroup generated by unipotent elements, then the assertion is that if you take a point G mod gamma, look at its orbit, let's write these as cosets, look at its orbit and take its closure, then this closure is always of the form f on G mod gamma, f G gamma mod gamma for some closed subgroup F. And in particular, if you happen to know that there is no such subgroup other than the whole of G, for this condition can so first of all, this is a closed orbit and it contains the H orbit, right? So if you know that there is no closed orbit for subgroups other than the whole group, then you will get that this original orbit without taking the closure that is actually dense. Okay, so and there is a duality between the H G gamma, another remark here, H G gamma mod gamma dense holds if and only if gamma G inverse H mod H is dense. This is a simple exercise for anyone for a beginning class of topological groups. So if Hg, this is dense if Hg gamma as a subset of G is dense, you take the inverse S, you get precisely this. So yeah, so that's sort of in the back. Let's keep that in the background. So that tells you in particular something analogous to what I mentioned here, namely that if you take an element G and for which GHG inverse, this is not contained in a closed subgroup F with the property that this has finite invariant measure, then the orbit of under gamma of the coset GH in G mod H is dense in G mod H. Okay, and the original thing that we were talking about here also, there are if you can look at these gamma orbits within this G orbit, and if this condition precisely corresponds to G orbit being dense, and therefore when that holds in the generalized framework, the gamma orbit will be dense. Okay, so this is only to sort of put the earlier result in the broader perspective into which it has gone from over the 3-4 decades during the interim. So there is quite a bit known in the direction of generalizing that to this general framework. That's would be an adequate message even if you did not follow some of the details here. The main observation that I would like to make at this point is that none of these results, whether the theorem that I reported here in this simple case or some of the more general results here, they are not effective results. Okay, we only know. So what does it mean? So in the case of the theorem, for instance, when I take p tuple from W, say V, and I'm looking at and suppose I know that condition is fulfilled, so I know that gamma V is dense. What does it mean? It means, translated into simple language, it means that for any other vector, any vector of V and epsilon greater than 0, there exists some gamma such that the distance between gamma V and W is less than epsilon, right? That for every W and epsilon, you can get a gamma such that this is true. Now the issue is if you start with an epsilon, how can you say how large the entries of this have to be? Maybe say, would it be enough to have would it, let's say now knowing that such a thing exists, you want to use your computer to check to find some gamma. So how far will you have to check? So for that you will need to know that well, okay, I can find gamma with a certain control on the size in terms of epsilon. That's an issue that comes up, and that's the issue of the action being the results being effective. So okay, it will be illustrated by the next result, which is so here are some effective results. Very effective results are known in very limited cases, and they're, as of now, they're very quite at an unsatisfactory stage. So that's the context that needs to be borne in mind. So one of the effective results that is known, this is a theorem of Michel Laurent and Nogueira, Arnaldo Nogueira. So this is, notice that this is a particular case of something that we were discussing already. Take lambda equal to SL2Z and take V in R2, then the following statements are true. Okay, so it says that there exists infinitely many gamma such that gamma V is less than or equal to size of V times gamma size of gamma inverse. Okay, so how does this relate to what we are talking about? This gamma V should be thought of as gamma V minus 0. So in other words, the other vector W I am taking as 0. So knowing the vector V, it's an irrational, so it has irrational slope, so I know that it is dense. In particular, the vector 0 can be approximated. Now when I want to approximate 0 as a vector in terms of vectors of the form gamma V, what this tells you is that it is enough to there are infinitely many stages, vectors for which this is less than or equal to, say, let's say norm of V is 1. So then basically you are saying that this can be made less than the size of gamma inverse. Okay, you only need to, if you want to get this gamma V is less than epsilon, you need to check only up to gamma of size epsilon inverse, right? That's the but this is something particular here. We took W equal to 0. We would like to know about other vectors as well, and more we would like to know about typical generic vectors. So now before we go to the generic vectors, let me take W with a vector with a rational slope. Then there exists, then the assertion is that there is a constant C such that I can make this difference less than or equal to constant times gamma raised to minus half for infinitely many gamma. So you can take larger and larger if you are looking for smaller and smaller things, then you can always hit upon one where this difference is less than or equal to constant times gamma raised to minus half. So if you want to yeah, okay, I think that should be clear. On the other hand, if I take W which with an irrational slope, then the result is weaker. Then in that case we can say the theorem only tells you that you can find gamma where this difference is less than or equal to constant times gamma raised to minus 1/3. So you need to take so if you want to make this less than epsilon, then it's not enough to take go up to epsilon raised to epsilon inverse, but we will actually have to go to epsilon epsilon raised to minus 3 because of this. So you need to the control that you have would be less. Of course, one might say that maybe that's in the nature of things that and you perhaps cannot expect better. But it turns out the one knows that one should actually expect better. This finding these gammas should be possible with any number here which is less than half rather than the particular 1/3. So this is an incomplete result. We don't know. About whether this can be improved, and the expectation is that it should be possible to improve it here with anything less than half. Okay. So before and the main result that I am going to talk about is in that connection, but before that let me also mention some developments that have taken place in parallel about that. And so there have also been other approaches. There are some authors I have mentioned, Duby-Kelmer and François Macourin, Barak Weiss, providing similar results, and their results are not for SL2Z, but in SL2R take other lattices. It's possible to have other lattices, in particular lattices for which the quotient is compact, etc. There is a whole variety of discrete subgroups for which the quotient can have finite invariant measure. And they study the question in that context. And however, if you specialize their results to SL2Z, then they are substantially weaker than there we saw. Instead of in place of 1/3 that we had, they would get something like 1/500 and something so on. So the results are much weaker. But nevertheless, on the other hand, they generalize to a more geometric kind of situation. There are also results of Anish Ghosh, Gorodnik, and Nevo on this question. These are in a more general framework, and because of that, they're forced to be they are weaker, and they depend on some representation theory, spectral theory, and so on. So that also limits the effectiveness that they can, the strength of the results that they can achieve out of that. Here I also skipped one of this observation here. The theorem of Laurent and Nogueira is sort of forced to be for SL2Z and nothing about SL higher NZ, because the techniques involved are closely connected with continued fractions. And for any vector, you have these are two coordinates. Now essentially what matters is the ratio, and so the ratio is a certain irrational number, and then the continued fraction expansion of that is in some way closely related to the gamma SL2Z action on R2, and the kind of questions that we are addressing here are related to continued fractions of the particular ratio. And they make heavy use of the continued fraction techniques, and so which are not available for when you have more number of variables. So that's a limitation which sort of forces you to look at SL2Z. With that, now let me come to, so the next thing I'm going to say is a joint result with Nogueira. Now we were trying to, our main aim actually was to try and see something, whether we can say something for SL and Z, even if not the complete analog in a way. But in that, that did not lead us very far. But in the process of that, we realized that if we sort of are willing to forego this condition of determinant, the determinant being 1, SL and NZ, we are always looking at determinant being equal to 1, because we are always staying in the group situation. But if we are willing to forego the condition and look at the action of gamma that I defined, to look at the semigroup of all n cross n non-singular matrices with integer entries, then we can do, not only we are able to answer the condition, answer the question of effectiveness, but we are able to sort of do it in a fairly complete manner in some ways that I'm going to talk about. Okay, let's go back to the setup of the theorem. So we have W is P copies of Rn, and we are looking at P vectors x1, x2, xp. Okay, so, and the conclusion that I have first written here with saying for almost all vectors. I'm going to say more about what this almost all stands for. It's not almost all in the general majority theoretic or ergodic theoretic sense, but it's a more specific set. But for the moment, let's just be content by saying that for almost all P vectors x1, x2, xp, the following holds. We can answer the question that we have in mind in the following way. So for any W, I have taken Y in W, there exists a constant C, which depends on X and Y, of course, such that if I take any number rho which is less than n minus p divided by p and epsilon, small epsilon, then for this data you can find a gamma in gamma satisfy such that gamma approximates gamma x approximates y to the extent of being distance being less than epsilon, and this I have a control on gamma which is of the order c times some constant times epsilon raised to minus 1 by rho. So rho has to be, notice that in the case of p equal to 1, this is simply n minus 1. Okay, so here maybe I already said it. Yeah, so yeah, in the case when n equal to 2, we get that yeah, this rho you can put for all rho, for any rho less than 1, you can have this condition satisfied, and you can compare it with the SL2Z case where we could say it only for 1/3 instead of 1/3. So long as you are for SL2Z itself, the expectation would be that you should be able to go up to 1/2, and for the larger semigroup, in fact, you can actually do better. You can take 1 here. Anything less than 1, for anything less than 1, you can find a gamma for which this holds. Okay, so there is another interpretation I have put in, which is sort of comparable to how the theorem of Laura and Nogueira was formulated. So in particular, if I take y which is not in the orbit of x, so this is a countable set that I want to exclude, then there exists a constant c prime and infinitely many gamma such that gamma x minus y is constant times norm of gamma raised to minus rho. So this is kind of these two relations are closely related. So if I have this, for instance, it means that epsilon raised to 1 by rho is less than constant times c raised to minus gamma raised to minus 1, and take therefore I will get that epsilon is less than constant times gamma raised to minus rho. So if this holds, then this condition is simply by solving the interchanging sides between this. So this, from this to here is immediate. What I am emphasizing in the second part is that if for something which is not in the orbit, if for y in the orbit, this can actually become 0. So you cannot do anything better. So but if it is not in the orbit, then you can only expect to approximate. You cannot actually solve it as an equation, but you expect to only approximate, and from that approximation you can do better and better. Why? Because once you find some approximation, this quantity is not 0. You take that as your next epsilon and find a gamma for which it is less than that particular value, and then so on. So when it is not in the orbit, you will keep getting more and more gammas which do better and better, right? So therefore there exists infinitely many gamma for which this condition is satisfied. Yeah. Okay. Now next I want to say something about what that almost all condition corresponded to. So here now you would have some time. So let me you may recall that a number, if you have a number alpha in R, this is said to be badly approximable, alpha badly approximable if alpha minus p by, if there exists delta greater than 0 such that alpha minus p by q is greater than delta by q square, right, for all pq integers q not equal to 0. On the other hand, if alpha is not badly approximable, we say it is well approximable. It is well approximable. On the similarly, anyway, that's the overall just the number theoretic context. But here, let me define directly what for p tuples of vectors. So we are going to define something which is actually corresponds to very well approximable, and the condition will be automatic from here. I will not. So take consider 1 less than or equal to p less than n always, and p tuple we define the homogeneous what we call the homogeneous exponent of this x. Okay, and it is defined to denoted by hx, and it is defined to be the infimum of all positive u for which there exists a constant c such that this relation holds for all non-zero integer matrices. And so for all non-zero integer matrices, omega times x, so this is a n cross n matrix, this is a n cross p matrix. Yeah. So it is greater than constant times now the size of this raised to minus u, and you can there is a certain the infimum of all such positive u's is called the homogeneous exponent. Now we say that p is projectively very well approximable if this hx, the homogeneous exponent, is at least n minus p divided by p, and this you recognize that this number is the same as that appeared in the theorem. Now this is in an analogy with classical notion of very well approximable approximable vectors. And also, okay, moreover, now notice that any p tuple like this, so when you think of this as a matrix, you can up to rearrangement of rows, you can always write it in this form. You can when you have well, for almost all of these, there will be a there'll be a block sorry, theta is a p cross p non-singular matrix up to for almost all of these up to interchange of rows. You can write them in this form. You can take a non-singular matrix here, non-singular matrix here, and you sort of want to have it separated, and you write the part at the top, you can write as xi times theta. This theta is non-singular, so whatever matrix you have here, you can write it in this form, and the relation between projectively very well approximable here turns out to be precisely that this matrix P should be a non-singular is projectively very well approximable if and only if xi, this is a matrix n minus p cross p matrix, which is very well approximable. So the matrix, the object that we have in our case can be first of all transformed into something like this, and that is projectively very well approximable if and only if this xi is very well approximable in the classical sense. Now, being very well approximable in the classical sense, one knows that is a very exceptional behavior. The set of numbers, for instance, and in particular, if you look at the set of numbers which are very well approximable, this is a set of Lebesgue measure 0. Similarly, when you take vectors or matrices which are very well approximable, that is a set of measure 0. And with the correspondence that I mentioned here, that also tells you that the set of vectors which are projectively very well approximable is a set of 0 Lebesgue measure. Okay, so if I take the x1, x2, xp, which are projectively very well approximable, that's a set of measure 0 because of this first of all, it is projectively very well approximable only if this xi is very well approximable, and that's a condition which is satisfied only by a set of measures n minus p cross p matrices of measure 0. And now when you put back the thetas, you will get the set of matrices of this form that satisfy the condition to be a set of measure 0. And the remark that I want to make is that the genericity condition that we had in the theorem, I said almost all, and that almost all consisted precisely to x being not projectively very well approximable. So long as the p tuple x1, x2, xp is not projectively very well approximable, that conclusion holds for holds as it is. So instead of this almost all p, I could have said this statement holds if I say let x be a p tuple which is not projectively very well approximable, and then I have this conclusion. Actually, there is a more general form of this theorem in which it's also a certain statement can be made about even for very well a class of very well approximable p tuples. But it turns out they still not the whole of whole set of p tuples. So in general, there's no analogous conclusion. What I want to say is that, as I said, this later conclusion we are able to hold, or we are able to establish for this particular constant, so long as x is not projectively very well approximable. Even for p tuples which are projectively very well approximable, the similar conclusion we can uphold by weakening this constant. That is possible, but not for unfortunately not yet for all p tuples. I mean, there is only because the function that is involved turns out to become infinity after some stage. So anyway, these are some slight technical points which I thought I'll just mention for the fun of it. I mean, to highlight the limitations as well. Okay, so now there are also other ways of looking at some of this. So for any p tuples x, y, notation about this number is something of interest. You look at all those real numbers, and for which gamma x minus y is less is norm of gamma raised to minus mu, so to say, for infinitely many gamma in gamma. So this is called the exponent of this pair with respect to the gamma action. And now this is here is a theorem in terms of this notation, which is actually not directly deducible from the initial theorem that I said, or even the modification that I indicated, but but comes from the same spirit. It is that again p between 1 and n minus 1, take a p tuple, and x1, x2, xp linearly independent vectors, and suppose that this condition is related to very well projectively very well approximable, but is here you can see it more explicitly. Suppose that you are looking at an x such that for any non-zero integral matrix, the omega x raised to p times omega norm of omega raised to n minus p is greater than, infimum of these is greater than 0. That's the condition which sort of holds the key for the results. Then for all y which are not in the orbit of x, we have the exponent is n minus p by p. Okay. So this sort of incorporates the here I don't have to say separately x, take x to be not projectively very well approximable, etc. Okay, so I want to say something about one of the important ingredients in the proof of this result. So it involves here is a statement which is the following result of Kneser and Birch, and we use the formulation as given by Meyer. There is a very well-known book of Meyer about on algebraic numbers and harmonic analysis, and this is a result reported there, which doesn't seem to be as well known as it should be. I think it's something that deserves to be much better known. This is a variation on the classical Minkowski theorem for in geometry of numbers. So you may recall that Minkowski theorem says that so we have Rn and Zn lattice Zn. So if S is a convex symmetric subset of Rn such that the big measure of S is greater than 2 power n, then S contains a non-zero integral point, right? Now there is an analogous question about when can we say that for a subset S, of Rn that V plus S, so this is V plus W in S contains an integer integral point. So no, it's you may recall that Minkowski's theorem is used for homogeneous Diophantine approximation, and to have inhomogeneous versions of that, you need a result of this form. That's the result of Kneser and Birch, and let me, since I already have it in this form, so let me describe the general construction of sets of this form, sets for which this such a conclusion holds. Now let S be a compact subset of Rn with Lebesgue measure mu of S greater than 0. This S is not going to be the same S, so keep that in mind. So such that no two points of S are congruent modulo integers. Okay, so now let n, this condition forces that the measure S, which is assumed to be greater than 0, is also less than 1. If you had a compact, okay, if it were because no two points are congruent modulo n, it's a simple exercise to see that the measure, first of all, the measure has to be less than 1 for a compact subset. Okay, this measure is less than 1, and now I take an integer bigger than or equal to 1 over measure of S. So this is an integer bigger than or equal to 2. There's some integer bigger than or equal to 2, right? Now the prescription is that you take S plus S plus S, etc. n times. This is the n here. So for instance, if you also assume that this is this set is convex, then this is simply n times S. And this is the answer to your problem, that then for each vector v, k plus v intersects Zn, for no matter what vector you take, the translate of k by v has an integer point inside that. So for instance, if you in this context, let me just tell you that here if you take a convex subset S, then if the measure is 2 power n, here it is 2 power n, but for this it suffices to have 2 power n minus 1. If you take a convex subset of measure 2 power n minus 1, you can have you can have sets of this form constructed in this way. No, I am not saying all subsets S will hold. But of course, if you take, if you have this is 1, 1, 2, 2, etc. Here, in between these, you can have convex sets of very large measure, arbitrarily large measure, which will not contain any integer point, right? But on the other hand, this construction, so long as you are prescribed that your set arises in this manner, then so long as its measure is at least 2 power n minus 1, whenever its measure is 2 power n minus 1, you will have the property that no matter where you shift it in the space, it will always contain an integer point. Okay, so what is the significance, what is the connection of this with our situation? It is the following. See, we are trying to get a gamma such that these two conditions are satisfied, right? Now, if you think of the space of n cross n matrices, all n cross n matrices, that's a vector space, and in that those with integers will correspond to the integer lattice, right? So forget for a moment, ignore the condition that you want gamma to be inside the to be non-singular. Okay, let's say first ask, can I have some matrix, n cross n matrix, for which this will be satisfied? Then it's purely a question of applying sorting out a question of the issue of this sort. That is, you want an integer matrix inside the space of n cross n matrices, such for which these are linear condition inequalities, so that the sets formed are quite nice convex sets. And your question, if you weaken it to just wanting integer matrices, then this is simply an issue of applying the theorem of Kneser and Bursch, right? Now, however, we have a catch. There is a catch here. So first of all, the set for which the theorem is applicable have to be constructed in a certain specific manner, and secondly, you want the determinant to be non-zero, right? You're just not going to be content with finding some n cross n matrix here. That's not in the spirit of the original question. So these are so that's where the Diophantine condition is involved. Yeah. So when you analyze what is, as I noted, a set of this form will not do. Then let's say you are looking at the origin. You want to look at various sets of this form. Now I'm thinking of this as the space of n cross n matrices and looking at various boxes. And when can I say that a convex condition of the type that I have in the theorem, that I want to I'm allowed to have one side somewhat large and other side rather small, and they should compensate each other to a suitable extent, and look at possible situations under which you can get the theorem in the condition in the theorem to be satisfied, and it turns out that corresponds to this Diophantine condition that I have written here. So that's where this Diophantine condition will come, and then further analysis shows that it's actually related to very well approximability in the classical sense, or the projective very well approximability in the sense that I mentioned. So going through all that, and then while doing that, it's also possible to pick things in a sort of way. So first of all, you will know where you are going to translate it, and then you want to make sure that this has a certain determinant, and then you can make sure that the translated thing also, the box is also to be arranged so that all the matrices in this have positive determinant. Okay, so non-singular, you can actually get determinant to be positive. I mean, there's okay, so that's roughly the idea of the proof. The details, of course, would not be possible to go into. With that, I think, let me see. So, with that, I will conclude. Thank you for your attention. It's only a semigroup.
So by orbit you mean just gamma p or?
Sorry?
By orbit of gamma, you just mean the set gamma v?
Yeah, gamma v with gamma running in gamma.
But it won't define the equivalence relation also.
No, it won't define equivalence.
Okay, let's thank Professor Dani.
Thank you.